So last time we were looking at two ways of searching through an array to find your needle in the haystack. We introduced the notion of pseudocode, in which you can think of these things in more general terms. Like, what is an actual collection? Well, in C, the only option that we have or that we've covered is an array. But in other programming languages, you have lists, sets, or other collections. Also, what is it that we're searching? Well, we could be searching for integers or doubles or strings. Or now that we've got structures, we could be searching for a particular airport, which we'll be doing next week after the break. The first solution that we came up with was this linear search, where we searched through the array and returned the index at which we found it, right? And we realized, well, that's kind of inefficient, because what happens with an unsuccessful search? You have to search through the entire array. And if there are n elements in there, then you have to make n comparisons to do that. If there are 1 million elements in there, then you have to make a million comparisons. If there are 1 trillion elements in there, you have to do 1 trillion operations. And then we introduce the notion of binary search, where if you've got a sorted array, in fact, let's bring that in. Let's see, where was it? Sorted array. Nope, over here. And I should have brought that up to begin with, but sorted array. There we go. What you can do is you can look in the center, right? Because it's sorted in ascending order here, you can examine the center here and say that you're searching for the element 42. Well, you look at 12 and say that that's not it, right? And so you immediately can cut out the first half of the array because 42 will be on this side if it's sorted, right? That means that you only have half of the array to deal with. You have a divide and conquer kind of strategy here. And you repeat it, right? You look at now that you've got a new array over here, you look at the center and you see 102, and you know that it's less. So you go this direction, effectively cutting out another half of it. So each time you're cutting it in half, cutting it in half, cutting it in half. You don't need to make nearly as many comparisons as with linear search. Here is the code. Now it's pseudocode that we developed before. Let's just walk through that. We've got 2 indices, a left index and a right index. The left index starts at the beginning, and because this is pseudocode, all of our elements start at 1 and go through n instead of 0 through n minus 1. The right index starts at the end, index n. While left is less than or equal to right, in other words, here are your 2 indices. While they've not passed each other, then you look at the middle element here, and that's just simply the average of left and right divided by 2. That's the average. Here I'm taking the floor of that, but in code I'm going to rely on integer truncation to do that for me. I'm taking the floor because what if it's like 5 divided by 2? 2.5. Is that a valid index? No. So we need to go down to the next valid index. If that's the thing that we're looking for, if a sub m is the key that we're looking for, then we're done, right? We found the element that we're looking for, and we output that element. Okay. Otherwise, if the thing that we're looking for is greater than the middle element over here, then we need to go to the right. We need to search in the right hand part of the array here. Okay. And the way that we do that is by updating my left index to be m plus 1. We don't update it to m because we've already checked m right here on line 5. Okay? Likewise, if we need to go left, then we update the right index to be m minus 1, right? Excluding m because we've already checked it. What I want to do is I want to take this pseudocode and I want to actually implement it in C now. Okay? Once again, with pseudocode, it's a sorted collection. Well, what is a collection? For us, that's going to be an array, right? And we don't use 1 through n indexing. We use 0 through n indexing. So we're going to have to update this and update this to n minus 1. We're going to have to translate, right? Or sometimes is referred to transpiling. Instead of compiling it, you transpile it, you translate it to another language. So you can take C code and translate it to Java code or something. Of course, it doesn't work that well in real life, right? All right, so let's go ahead and document this first. Performs a binary search, and that's what this is called. It's called binary because I'm cutting the array in half each time. Binary is 2, right? 0, 1, right? High voltage, low voltage, and there are only 2 options, so I'm splitting it in half. Performs a binary search on the given array of size n for the given key element. Right? Returns unindex upon success, and then upon failure, -1 if no such element. Okay? Now, why did I have to emphasize here unindex? What if I'm searching for 42 and there are 5 copies of it? Am I guaranteed to find the first one? No, I could find this one or that one or that one, right? So I'm just going to return unindex at which you can find that element, right? A -1 otherwise. All right, same thing as up here, all right? Except that we're going to call it now binary search. Binary search. And we're going to have to transpile or translate this over here. So I'll have 2 indices, a left index and a right index. Int left is equal to something. Int right is equal to something. Instead of L and R, I'll use the full full, I could call it left index, right, if you want to. I'll just go ahead and, yeah, let's go ahead and do that. Left index and right index, okay? To make it absolutely clear what that is representing. Now, my left index is going to start way at the beginning, which is 0. My right index is going to start all the way at the end, which is n minus 1, okay? We've got lines 1 and 2 translated. Now I need to translate that while loop. While the left index is less than or equal to the right index, right? Then I need to compute that middle index right there. M is equal to L plus R all over 2, the average of them. If you've got two numbers on a number line, how do you get the number right between them? You take the average, right? Right? So int M, middle index, I'll call it, to be consistent, is going to be left plus right divided by 2. All right, there. Now, are we going to have an integer truncation issue here? Yes, and that's a good thing. Because, again, if you have 5 divided by 2, 2.5 is not a valid index. So it will truncate down to 2, giving me my floor. I will note here, careful, this risks overflow. Right? If for very, very large arrays, if you've got like 2 billion elements in your array, suppose that left and right are close to 2 billion. 2 billion plus 2 billion. What is that in C? Remember that it's an integer. Can you represent 4 billion using an integer? Only 2.147 billion. It wraps around to a negative value, giving you overflow. So be careful that this risks overflow. There's a better way of doing it. Read the book. I don't know if it's in Zybooks or not, but it's definitely in my book. Right? But we're keeping it simple, so we'll go ahead and use this. What is it going to be? It's right minus left divided by 2 plus left. Right. So here's the safe thing. Right minus left, divide that by 2 plus left. Now, if you take out your algebra hat and you simplify that, you'll end up getting this over here. But this one does not risk overflow. Okay? All right. Just a technical thing there. All right, I've got my middle index now. Right? Now what I need to do is I need to check, is that middle index element equal to my key element over here? Okay? So if array sub middle index is equal to my key value, right, as indicated up here, right, then I've found what I'm looking for. I will return the middle index, the index at which I found it. Okay? Else if the thing that I'm looking for, the key here, is strictly greater, then it's going to be on the right. Right? So if this is less than the key element, then I'm going to search on the right half. ... Meaning that I'm going to update my left index to be middle index plus 1. So left index is equal to middle index plus 1. Right? And then the only other possibility, it's either equal, strictly greater than, or strictly less than. So actually, let me write that out right explicitly. If the thing that I'm looking for is less than the middle index element, right, then I need to search on the left half. And by the way, everybody knows this algorithm. You play it all the time in the numbered guessing game. In fact, you implemented the numbered guessing game in like Lab 4. I'm thinking of a number between 1 and 100. What do you guess? 50, right? Because I'm going to tell you high or low. You don't go 1, 2, 3, 4, 5, right? That's going to take forever. Instead, you choose the middle element, and then I say, oh, it's higher, because you cut out 50 possibilities, right? You've used this trick all your life without even thinking about it or calling it binary search. Right? Hopefully, you've seen that game before, right? The guessing game. I'm thinking of a number between 1 and 10, and then you always start in the middle, right? Right index will then be updated to middle index minus 1. Right? I'm going to search on the left half. I'm taking the right index and I'm moving it down to below the middle element. Okay? I'm not done. What happens if I don't find what I'm looking for? Unsuccessful search. And as per my documentation, it'll return a -1. It breaks out of this while loop when left and right, when they've met and exceeded each other. When they're equal, of course, it will still execute one more time to check to see if that thing, this is equal, so divided by 2 will give me that the middle index right there, right? It'll still look at that value, okay? All right, so we need to check to make sure that it's there or not. Let's come back down here, and let's change this to our binary search. Okay? Is it going to work? Let's find out. CSE is 42 in there, by the way? Hopefully I didn't screw anything up. Uh-oh. Left and right. Oh, not left and right. It's what? Left index and right index. There we go. All right. 42 not found. Looks like it works to me because 42 is not in there, right? Let's search for 7 instead. 7 not found? I see it. It's right there. What's wrong with this array?
Not sorted.
It's not sorted. So what's going to end up happening? It's going to come here to the middle element, say it's this one, 45, and it's going to say, hey, you're searching for 7. I'm assuming that this is sorted, so where am I going to search? On the left part. Are you going to find 7 on that left part? Nope. So the key thing here is that binary search has to have a sorted array. We'll get there, all right? But before we get there, let's understand this a little bit more and see how much better it is than linear search, right? If it's not better than linear search, then why are we even looking at this, okay? First of all, I'm going to highlight the work that's being done here. Just like linear search, the thing that we looked at with linear search was with respect to this, this comparison right here, right? Is this element equal to the key element? In which case we said, yes, return it, right? If we got lucky, we only had to make one comparison. If we got unlucky, we had to make n comparisons the entire array, right? Here we're going to assume that we're going to always be unlucky and go the full 9 here and end up with a unsuccessful search, right? But what is the work that we're doing here now, right? There's a comparison, and there's a comparison, okay? So for each iteration of this while loop, we're doing one comparison, right? And here, we can get rid of this. Get rid of that, and then erase. There we go. All right. So each iteration makes 2 comparisons. Okay? But I'm going to simplify that. In my actual code, how many comparisons was I actually doing? 1, 2, and then 3. But is that third one absolutely necessary? No, it's an it's an exclusive or. I could have gotten rid of that. In other words, I could have said, just leave it as else. I'm leaving this because I want it to be explicit for the demonstration purposes. So we've taken something that's 3 and down to 2 comparisons here. At the end of the day, though, I'm going to roll those together. I'm going to simplify this. I'm going to just say that there's one comparison. Because at the end of the day, what we're going to do is we're going to call a function. Right? We're going to call what's called a comparator function. We're going to take these 2 things, not integers anymore, not doubles, not strings. We're going to take these 2 things and we're going to hand it off to another function. That function is going to return something positive, negative, or 0, depending on the relative ordering of these things. You've seen this before. strcmp. If I give it a string apple and I give it a string banana, it will return something negative because A, apple comes before B, banana. Right? If I gave them in reverse order, it would give me something positive. If I gave it apple and apple, it would give me 0 because they're equal to each other. Okay? That's how we're going to end up making our comparisons. We're going to make actually one function call rather than making an explicit comparison. Right? So I'm going to simplify it immediately. Suppose that we make one comparison per iteration. That means that the number of comparisons is equal to the number of iterations of the while loop, right? So this while loop right here, I'll highlight it. How many iterations does it go for? Okay. we're not going to go through a full analysis. We're going to go through a partial analysis. Let's think about the iterations. On iteration 1, let's think about the size of the array that we're looking at. The size of array. Right? Now, initially on that first one, there are going to be n elements in there. But on the second iteration, what have we done? We've cut it in half. Right? There's going to be n divided by 2 elements in there. Right? On the third iteration, we cut it in half again. Right? Now, if you cut something in half twice, how much is left? A fourth. Right? So n divided by 4. Right? What if on the fourth iteration, it's n divided by what? 8. Right? Okay? Dot, dot, dot. On the ith iteration here, you have cut it in roughly, right? We're off by 1 here, but I don't care. Right? I want the math to look nice, right? Roughly n to the divided by the 2 to the n, right? If you want to, you can start your iteration at 0 instead, and then you'd be completely on, right? Right? All right. How many iterations do we go to then? Like, when does this actually end? How many iterations? Well, this ends over here when what? The left and the right are going and going and going. Finally, it's of size 1. We make one more comparison to make sure that that's the thing that we're looking at. So the second to last iteration here will be when the size of the array is cut down to 1 here. Okay? For what I is that true? All you have to do is say 2 or n divided by 2 to the I is equal to 1. How many times do you have to cut it in half in order to get an array of size 1? Right? Apply some algebra. I can take that 2 to the n, 2 to the I, excuse me, to the other side. Now, I think it's algebra still. How do I get rid of that 2 so that I can isolate I, solve for I? Yeah, log. Right? Log, what base though? Base 2, right? Because this is not base 10, like humans, 10 fingers, 10 toes. It is not base E, like mathematicians. Instead, it is base 2, because it's computer science. Right? All of our bases are going to be base 2, to the point where we won't even write 2. We'll just implicitly say log of n, that's going to be implicitly log 2. It doesn't really matter. Right? Here's an aside, and here's your math lesson for the day. I can always change a base, log base b of x, using the change of base formula. Log base a of x divided by log base a of b. Right? This right here is just a constant. Right? So this is equal to some constant times log base a of x. This is why we can take our 10 fingers and 10 toes that we count base 10 in, and then we can translate it to base 2, a binary, 0, 1, that a computer can understand. But what about those weirdo mathematicians? E. What is that equal to? 2.71, blah, 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 blah. Is there a counting system with 2.71 characters? Does that even make sense? Nope. That's not their purpose. What is their purpose in math? Why is it the natural log? Natural. Right? It's only natural if you're a mathematician. So you'll have to put on your calc hats for a second here. What is the first derivative of e to the x? E to the x. That's why it's natural. There is a constant coefficient out here of 1. Right? That's the only base for which that's true. If you were to try to take 2 to the x and take the first derivative of that, you would end up having 1 over natural log of 2 times 2 to the x. In other words, you'd have a non-1 constant sitting out front here. This is why mathematicians like E, because it makes all their equations nice and pretty. Right? You only need this one symbol. Right? We live over here in the computer science world, where all our bases are base 2, because we cut things in half, because we count 0, 1, 0, 1, right? Etc. Okay, so the number of iterations here is going to be log n, right? And since we said that the number of comparisons you did 1 on each iteration. 1, 1, 1, 1, dot, 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 1. If I were to add all of these up, what would I get? Log base 2 of n, or log n. Okay? Now let's think about that in the same terms that we thought about linear search on Monday. With linear search, if we went from a size n, well, actually, the first thing that we did was we graphed them, right? So let's graph them again. So here's n. Tell me what the graph of log n looks like. Yeah, it's like extremely slow growing here. Log n. Right? So already, which one of these is better? Right? Remember what we're quantifying here. N, this is the size of the array. What are we quantifying on the y-axis? Comparisons. In other words, work. Or another way to put it is time. Right? Does it take 5 nanoseconds? 5 nanoseconds, or does it take 50 million nanoseconds? Or 50 seconds? Right? Now, which one is better? Is higher better or is lower better? Lower, because it's quicker. Right? So, quicker. Faster. Better. Right? Already we're seeing a huge improvement. How much of an improvement? Let's look at it from the calc perspective. Right? What was the first derivative of n? By n, x dx is going to be 1. Right? In other words, it's a constant rate of growth. That's why you look at that in calculus, right? That's why you look at the first derivative, because it gives you the rate of growth of a function. Now, you might not know what log base 2 of n, that derivative is, so I'll tell you. It's 1 over natural log of 2, n. Right? In other words, some constant times 1 over n. Now, as n grows, tends towards infinity, what happens to this denominator? It gets bigger and bigger and bigger. If the denominator is getting big, what about the whole thing? 0. It's going. It's limiting down to 0. In other words, the growth rate goes down. Right? That's huge. Here it stayed constant. Here it actually goes down as you do bigger and bigger computations. The rate of growth, not the time. This is still monotone increasing. Right? Another way of looking at it. If I went from n to 2n, in other words, I went from 1 million elements to 2 million elements. If it took me time t before, if it was linear, it would take me time 2t now. That's not what it looks like here when it's log, right? So this will end up being log of 2n. Now, once again, you're going to have to review your algebra. What is the identity of log AB? Log A plus log B. So in this case, I'm going to switch them around. Log of 2, right? In other words, it took time t before to do it when it was n. That's log n. That gives me time t. Plus, now tell me about this. Log implicitly base 2 of 2 is equal to what? 1. Right? You only do one more comparison going from 1 million elements up to 2 million elements. If it was linear search, you would be doing 2 million more operations. 2 million more operations. Here with binary search, you're only doing one more operation. Right? One more way of looking at this. Suppose that we had a very large n. Say 1 trillion, or 10 to the 12th elements. Right? With n, right, linear search, we would end up doing 10 trillion, that is 10 trillion comparisons. Right? 10 trillion, okay? What about binary search? N is equal to 10 to the 12th, but the behavior here is log of n. So, One more time, I'll ask you, and this is the end of the math today. Right? What's another log identity? Log of x to the y, what can I do to that y? Goes out front. Log base 2 of 10. This is less than 40. 40 comparisons to search 1 trillion things, right? That's 1 trillion. Yeah, that's 1 trillion, right? So 40 comparisons versus 10 trillion comparisons. Is there really any comparison? No. This is exponentially faster, right? Which is why we like it. Okay? All right. So, binary search blows linear search out of the water. The problem here is we've got to do something about this here. Right? Which app am I using? I'm using GoodNotes 8 or something like that on my iPad. Right? There's a question online. Right? All right. So, what could you do with this? Of course, you could sort it and manipulate it and stuff, but I want the code to do that for me. Okay. So we need to come up with an algorithm to do this. Let's go ahead and let me find an unsorted array that we can work with here. All right, that's gonna fine. We'll do this. There's already some smooch on it. I should clean that up. I don't know why that's there. It's permanent though. Anyway, here is an unsorted array. How would you go about sorting this? Suppose it was just a bunch of Post-it notes, right? That you could pull up and manipulate and move around and stuff. Right? Let's start at the beginning. Right? What should go here? Should 42 go here? No. You know that there's something less than 42, right? What? 4 is less than 42. Right? Okay. 9's not less than 42. 4, there's another 4 right there. 102 is not less than 42. 34 is less than 42, but it's not less than 4. 12, 2, oh, 0. Okay. 0 is the least element. So let's go ahead and swap these two around. Right. And we'll end up with 0, 4, 9, 4, 102, 34, 12, 2, and 42. Okay. Should I ever mess with 0 again? Nope, it's where it needs to be. Let's do that again. Right? What should go next? What should go second? 2? All right, how did you find that out? Right? As a human, you looked at it and said, ran all the way over to 2, right? Computer can't do that. A computer has to be rigorous. A computer, you're rigorous in your viewing, but computers don't have our human vision to look at a small number of things and immediately get it. Right? You have to tell a dumb computer how to go about doing that. So we'll start with this one, 4. Okay. 9 is not less. 4 is not less. These are not less. 2 is less. Okay. 42 is not less than 2. So the next thing that should go there is, there we go. 2, we should go ahead and swap those, giving us 0, 2, 9, 4, 102, 34, 12, and now 4 is over here, 42. Tell me about 0 and 4. Or, sorry, 0 and 2. Should I ever touch those again? Nope. Both of those are where they need to be. Let's do one more iteration of that. All right. What should go right here? 9. Okay, maybe. 4. Okay, 4 is less than 9 so far. 102, that's not less than 4, not less than 4, not less than 4. That's equal to 4, so we don't update that. 42. All right, so we should swap these, right? Leading us to 0, 2, 4, 9, 102, 34, 12, 4, and 42. Once again, we have sorted the first 3. This is the first iteration, second iteration, third iteration. On each iteration, we're finding the minimum element among the remaining elements. Right? This is called selection sort. Right? Think about it more generally, though. All right, actually, no, I don't want that. Let's go with this. All right. So here, sorted. All right. In other words, we've sorted 0 through, say, I minus 1. Right? 0, 1, 2, up to I minus 1. Now what we need to do is we need to find who belongs in the ith position here. Okay? How am I going to go about doing that? I plus 1, I plus 2, right? Dot, 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 up to n minus 1. What I'm going to do is I'm going to assume that this is the minimum element. Then I'm going to run j, running from I plus 1 to I plus 2 to I plus 3, dot, 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 all the way up to here. And I'm going to look for the minimum. You've all done this before. You had to program a function to return the minimum value in an array at some point. Okay? All you're doing now is you're finding the minimum among a subarray. You're ignoring all of this stuff and finding a minimum among the I up to the n minus 1th element. All right? Oops. Yeah, that's it. How many times do I repeat this? I guess here, let's outline it first. So find the minimum among elements a sub I through a sub n minus 1. Right? Then what do? Swap it with a sub I. Right? So suppose that this ends up being the minimum right here. Right? This ends up being the minimum. What do? I swap these two things. Swap. Right? And then I continue. That is the general idea. How many times do we repeat this? N times? We could, but we could actually get away with n minus 1 times. Think about, fast forward to the end, right? I have now sorted 0 through, say, n minus 2. And here's n minus 1, right? The last guy. Right? Everything over here is sorted. What about this last guy right here? Yeah, it's where he needs to be, right? Because I've put all the n minus 1 or n minus 1 elements that are smaller than it, I've ended up swapping them all over here. And this guy has basically bubbled up to the top for us. Right? So let's program this. Yeah, we've got plenty of time to program this. Right? All right, we're going to call this selection sort. Let's come up here. Right? All right, sorts the given array, and yeah, there we go. Sorts the given array using selection sort. Right? That's it. Right? I'm not going to return anything because you're giving me an array and I'm going to manipulate its contents and reorganize it so that it's sorted. Right? So we'll call it selection sort. Selection sort. There we go. Can I give it const int star array and int n? Can I make it const? I'm making changes to it. It better not be const, right? Okay. So how many times do I repeat this? I repeat it n minus 1 times. So for int I equals 0, I is less than n minus 1, I plus plus. This will repeat n minus 1 times if I because this is n times, as we've all seen in an idiomatic for loop. This is n minus 1 times, right, because it starts at 0. Right? All right, let's outline this. Find the minimum among elements I through n minus 1. Okay? I'm on this step now. Suppose I've already sorted the first I minus 1 of them. I'm going to start at j, and then I'm going to find j being I, and I'm going to find the minimum among the rest of them. Right? So let me go ahead and create a min index, like we've done before, and I'll start it at I, right, because that's what I did over here. I'm starting this index right here, and I'm assuming that that's my minimum. Then I go through the rest of these things, j starting at I plus 1 through and including n minus 1, to find to see if I can find something less than it. Right? So another for loop. For int j starting at I plus 1, j is less than n, j plus plus. There we go. Right? If the array element at the min index, let's go with j. If the element at the jth element is less than the min index that I found so far, right, then a sub j is smaller. Right? update, ... What do I update? Min index, and I found something smaller than it at index j, so I set it equal to j. Right. Once I've found the minimum element, I now swap ace of I and ace of min index. Okay, that means I need a temporary variable, ace of I. Set it equal to ace of I. Ace of I will then take on the value ace of min index, and then ace of min index will take on the value of temp. Oops, temp. Right. All I'm doing is swapping them. Taking one value and putting it in the temporary variable, putting this value over there, taking this value and putting it over there. Okay. All right. Then I return at the end. Right. Return. Okay. Let's come down here and see if it works. So even before this binary search here, what I'm going to do is I'm going to call selection sort on array. There we go. And then I'm going to print the array. I think I've got that utility up here. I stole it from Hack7. Yeah, print array. Okay. So let's print it out to make sure that it actually works. ARR sub n. All right, GCC this. Oops. Print array, sorry. All right. And selection sort. What's wrong with that? I spelled it correctly, didn't I? I copy-pasted it, I think. All right, too few arguments, sorry. Too few arguments. The array and then n, the size of the array. GCC. Oops, and I called it A instead of ARR. All right, I've got ARR, 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 R, R, R. Is that all of them? Yep, good. All right, so here's the contents of that array, remember, right? 54, 87, 63, ... 7 should now be at the front, and I think 91 should be at the end. Right, there we go. 7 is at the front. Does that look like it's in order to you? It does to me. Oh, hey, we found 7 now. Because we were able to sort it first, this binary search that is searching for 7, right, found it at index 0, right there at the beginning. Right? Likewise, if you wanted to search for, say, let's do some regression testing here, 75. Right? Does that still work? There. It's at index, that's nothing, go away. That's at index 7, right? 7, 8, 9? Yep. What if we searched for the largest element, 91? Let's make sure that that works too. Yep, we found it at index 9. What if we search for something that we know doesn't exist? That should still come out as an unsuccessful search, and it works. Right? This search part right here is exponentially faster. That doesn't matter if this kills us right here. Right? If you're only going to search it once, maybe it's better to use a linear search because this represents an investment. Right? This could actually take a lot. In fact, let's analyze that algorithm so that we can understand what's going on there. Right? I think I've got some pseudocode for this. Let's find it. Selection sort. I don't? No. All right, I have it over here then. There it is. There's the pseudocode version of selection sort. Now remember the difference between code and pseudocode. We're starting out at 1, right? So our indices will run from 1 up to n-1 inclusive. I'm not using equals here as the assignment operator because not all languages do that. 99% of them do, but there are some weird languages that don't do that. Pascal, I think, uses this. I could be wrong on that, but I think Maple TA uses that. Haskell, I think, uses this or something. Right? Or some, I don't know. Maybe it's R that I'm thinking of. Anybody do statistical stuff with R? No? Okay. Anyway, it doesn't matter. We're going to assume that this is the minimum element, and then we go through the rest of the elements, finding something that's less, and we update that, and then we swap it down here. Those 3 lines of code are simplified with just regular old English. Swap that thing and that thing, right? I assume that you know how to do that in your programming language, if it's Java, if it's C, if it's Python, right? All right, we want to look at this with respect to the amount of work that it's doing, right? So what would you focus on here? There's a for loop, right? There's an assignment. There's another for loop, right? There's a comparison. There's another assignment. There's a swap. What would you want to focus on? What's your instinct say? So something that's only done once for each of the outer for loops, there's something more common, right? If I've got a loop within a loop, that kind of tells me that I'm doing more work within the loop somewhere here, right? That's what my intuition says anyway. So what are we doing here? Well, is line 5 always executed? No, it's only ever executed if this is true. But however, this comparison right here is always executed. That's what I'm going to focus on here. Okay? So, I don't know. Do we want to go through the full analysis here? It's going to be more math. You want to do some more math today? Yeah? Okay. All right. So, let's highlight, as long as there's one yes, I will agree to do math, right? All right, how many comparisons do we do just in this one block here? 1, okay? Now, zoom out. How many times do you execute that one block with respect to this for loop here? We execute it with j running from I plus 1, I plus 2, I plus 3, ... all the way up to n. That is a summation. J running from I plus 1 up to n of 1. All right? If you haven't seen the sigma notation, has everybody seen the sigma notation before? If not, no. All right, maybe not remember it. All right. All right. Anyway, we run from j, I plus 1 up to n. And we're summing 1 plus 1 plus 1 plus 1. Now, zoom out again. We've got a loop. We've got a block within a block within a block. How many times is that executed? It's going to run from I1 up to n minus 1. So that is a summation within a summation. 1 up to n minus 1. Right? Right? N minus 1? Yeah, there we go. Okay. Now you just have to solve the summation. If you want to, you can throw it into Wolfram Alpha and it'll solve it for you. Right? But let's actually solve it. Think about this one. 1 plus 1 plus 1. How many times? 1 plus 1 plus 1 plus 1 plus ... plus 1. Right? Well, let's start counting these up. This will run from n, or from I, say I plus 1, up to n. If I started at 1 instead, 1, 2, 3, ... Then how many 1s would there be here if I started at 1? 1, 2, 3, all the way up to n. But I didn't start at 1, did I? I started right here. Right. How many things are over here? Or, sorry, I minus 1. Right. Or, sorry, no, I. Let me get rid of that I. Right. So, if I'm summing up n things, n 1s, then I would have n. But I didn't sum them all up. I didn't include I of them. Right? So right here, the number of 1s is n minus I. That's this summation right here. Right? So this is equal to, don't lose your outer summation, 1 up to n minus 1 of n minus I. Okay? There's the thing that we now need to solve. I've taken one summation. Is that copy? Hopefully that... Oh, no, that's not copy. Cancel it. Okay. Oh, I don't know how to get rid of that stuff. All right, I'm going to rewrite it. How do I get you to go away? Come on. Can I just get rid of you? No, I don't want to enable any of that. All right. Let's close. Full screen. No. All right. Screw it. All right. So brand new page here. Summation of I equals 1 up to n minus 1, oh, sorry, n minus 1 of n minus I. There. Summation of sums is equal to the sum of summations. I could break this up into two summations. I is equal to 1 up to n minus 1 of n, minus I is equal to 1 up to n minus 1 of I. Okay? Now think about this first one. This should be pretty easy. I've lost all my I lost my highlight tool too because of this crap. Come on, window. Nope. No thanks. Go away. All right, there we go. Restored. All right, there we go. All right. Brand new features. It installed an update since I hadn't used it since spring. What about this thing right here? N plus n plus n plus n. How many times? You go from 1 up to n minus 1, so it's going to be n times n minus 1. Right. What about this guy right here? This is 1 plus 1, or sorry, 1 plus 2 plus 3 plus dot 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 plus n minus 1. Has anybody ever seen that summation before? You have? It's called Gauss's formula. Right? Here's an aside. If I sum the natural numbers 1 up to n, this is 1 plus 2 plus 3 plus dot 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 plus n. Gauss came up with a closed form solution for this, n times n minus 1 all over 2. Right? The apocryphal story was that he came up with this idea when he was a grade schooler. He was told by his teacher, he was annoying his teacher, so he said, go off in the corner and sum the numbers 1 up to 100, right? And thinking it would take him a while to do it. Well, he just immediately answered 100 times 99 divided by 2 is going to be like 50/50 or something, right? 5,050, or no, something like that, whatever it is, right? Right? 50/50? That doesn't sound right. Yeah, I don't know, whatever, right? I'm not Gauss, right? Anyway, that's the story. We don't go up to n. Instead, we go up to n minus 1. So if I plug that into Gauss's formula, I get n times n minus 1 times n minus 1 minus 1, so it's minus 2, all over 2. Okay? Something like that. Dot, dot, dot. You're eventually going to get down here to, what can you do? 2 over 2. Now you've got 2. Now you've got, this will take care of 1/2 of this. Right? Anyway. Wolfram alpha. So I'll show you how to do it in Wolfram alpha too, in case you ever need to do it. Right? Here's the original summation. Sum of I equals 1 up to n minus 1 of sum of j running from, what was it again? I plus 1 up to n, right, of 1. Oops, I forgot a parenthesis there. There we go. There we go. Just making sure that that's correct. That's correct. It interpreted it correctly. And there we go. 1/2 of n times n minus 1. So 1 n times n minus 1 all over 2. There it is. Right, simplified. Okay. Now, before we leave here, well, actually, no, we'll save it for next time. But this is going to end up being, something like n squared. Right? In other words, it's quadratic. It's not linear. It is not logarithmic. It is something completely new. How bad is that thing? And we'll find out on Friday. Okay. It's really bad.